Today's our first video on these series of videos about numerical methods in thermofluids. We're gonna start off nice and easy with one-dimensional heat transfer problem. The problem we're trying to solve is this one. Variation of the temperature in respect to time should be equal to alpha Laplacian of the temperature. So this is a partial differential equation, and for us that we're looking in this video, the one-dimensional case, we're going to be writing this as such. Now, since alpha is a constant for us, I can just set it as 1 for simplicity, right? In this case. But if it isn't 1, you just put a number here, 5, 2.5, whatever it is. So to solve this problem, it's a partial differential equation. We're going to use the finite differences method, which consists of approximating both derivatives, this one and this one. So we're going to say that the variation of temperature in respect to time is approximately equal to temperature. But now, see, temperature is a function that depends both on time and space. So if I want to say temperature at a specific point I, I'm going to put it a little I here in the bottom, at the bottom. And if I want to say at a specific point in space, is going to be I in the bottom. And then if I want to say a specific point in time, I'm going to put K at the top here. So if we want to approximate this derivative, we can use the principle of calculus using the slope of the tangent line and calculate it as such, right? It's pretty intuitive, no problem. And then a delta t. The closer, the smaller your delta t is, the more accurate this approximation will be, right? So yeah, and then we have that del squared t over dx squared. Well, if you expand this in the Taylor series, there's going to be a documented description of the video, probably, that I wrote, in which I explain where exactly this approximation comes from. But this should be t I plus 1, ti plus 1k minus 2 ti k plus ti minus 1k divided by delta x squared. Now, if we plug in these approximations into our original function, what do we get? We get, well, something like this. We can see that ti k plus 1 minus ti k over some time should be equal to ti plus 1k minus 2 ti k plus ti minus 1k over dx squared. Now, you should be asking yourself right now, okay, what the fuck do we actually want from this problem, right? Well, for your bar over here, this is our bar one-dimensional heat transfer equation problem, we know at time equals 0 what, apples, banana? No, 0, just 0. There is not 0 seconds because we non-dimensionalize the equation, so it's just 0. no units needed. So at time equals 0, we know the temperature at every single point of the bar. So we know everything at the start of time. So our question really is, what will happen in the future? So what will happen next? And what term tells us what's going to happen next? It is this term over here. Oh, let me put another color so it's easier to see. It's this term over here. So we can rewrite this equation as being, holy fucking shit, as being ti k plus 1 should be equal to ti k plus delta t delta x squared that multiplies ti plus 1k minus 2 ti k plus ti minus 1k. Okay, so this is our bread and butter. This is going to be the heart and soul of our code that we're going to use to solve this problem. This is what we're going to iterate over time, right? Perfect. Let me hide this. We can go back to this later. I love Epic Pen because of this. We can go back to this later and look at our equation. So first things first, we just get our libraries. Import numpy as np. What the fuck? Import matplotlib.pyplot as plt. And then these two libraries, I'm pretty sure all of you guys know what they are, but this third one maybe not. So from numba import ngit. This is optional. This is optional. Import ngit. optional will make the code faster. So this library makes it so Python isn't as slow as it actually is. So it compiles some functions that you write in a lower level language to speed it up, because Python is so fucking slow. And you know, my advice would be to actually don't use Python if you're planning on doing numerical simulation. Sure, Python has its values in other areas like AI. I think Python's widely used, but for numerical simulations, Python's super slow. I would recommend Fortran. I'm using Python right now because I started on Python, so I'm just finishing what I started, but then I'm gonna move to Fortran or Julia or C++ or whatever. So we're gonna say now simulation parameters. So what are the simulation parameters? Well, we have a length of the bar. I'm gonna set it to 1 for simplicity. Gonna set it as 1 for simplicity. We're gonna have the number of points in our bar, which I'm gonna say it's 100, whatever. We also have our, what was it called? Initial time, which should be just 0.0. Final time, t final, should be what? Should be like the time it takes for your problem to reach a steady state. But you know, I'm gonna set it to here to 5 seconds. I can like put a realistically like a high number here and not weigh down the simulation way too much because of Numba, but you don't have to use Numba if you don't want to. It's just an habit of mine. So dx. So what is this? The step in space that we're gonna take? We're gonna take L over dx. This is pretty. Sorry, nx. This is pretty standard. And for time is a little more complicated because there's a numerical limitation to the time step that you're taking. If it's too big, the simulation just will just diverge, you know. So you want to make sure it's as small as it has to be, and this equation will tell you just that. This will be on the PDF again if you want to know where this comes from. It's really important to understand, but I'm not gonna say here to make the video super long. We have the initial conditions. Oh yeah, first we need to discretize the space. So x equals to np.lim space 0, 0, 0 L dx. So this is a very widely known line of code. That's it's n. Actually, it's nx plus 1 here. I got ahead of myself a little bit. Widely used line of code to just discretize the space and the steps we're going to take, and then we just create a np.zeros in x. We here are creating our temperature array, but you know, you don't need, like, this will change from problem to problem. We can even make it like the classical, this is like the first problem for heat transfer you guys take. It's np.sine np.pi over 2 times x. And here I don't need to, like, this is a really easy problem to see if it's right or wrong because you know exactly what the bar should look like, the temperature field. So I recommend you try this one first. If you want to try anything fancy later, you can do that. And here I don't need to indicate that t is an array because, well, t is x is multiplying this, so x is an array, so you don't have to do this to indicate it's an array. So like the shit you can get away with Python is fucking crazy. And then we just have, the temperature at the extremities of the bar. So at the far left and far right, I'm gonna say the temperature at a point 0 should be equal to 0. Why not? And then t of nx should also equal 0. And then you can also write this as being -1 here. But I see some people do that. It apparently works, but I don't know, it seems kind of unintuitive. And sometimes Numba, it's a bit of a bitch when it comes to writing stuff that is illegal in other languages but legal in Python. And this is one of those things, so I try to avoid that because of Numba mostly. Right, and then we have a T temperature new, which is gonna be our np.copy T. So why am I doing this? Why am I creating this line of T new equals NP copy T? Because our temperature into the future depends on the temperature of the past. So you want to make sure whenever you're calculating the temperature in the future, you want to take the time step, the previous temperature, you know, the temperature at the previous time step. So this ensures that this will happen. And now we can do our time temperature temperature evolution for time loop over time loop. Now if you didn't take numba, just forget this and JIT. This is just to call numba to make it faster, but you don't actually have to use it. We define a function def calculate temperaturi that calculate temperature, and then I'm gonna set the parameters later. So we're gonna have a while loop. Oh god, where is the, sometimes my keyboard is in another language, so I forget. So while t is less than t final, since we're doing this problem over time, we want to check every single point in the bar. So for I in range, and then we just set it as 1 in x, because this will make sure we don't start at point 0, and we end within the bound of our domain, right? Which is what we want. We just plug in that formula. So t new, what was the formula again? Let me see. So t new T new is the temperature at new time, should be Ti, should be T, where's the Ti plus dt, dt over dx squared times T I plus 1. Let me erase this so I can, let me erase this so I can like see what's going on here at the code properly. We're not gonna need this anymore. Just the formula will suffice. Ti plus 1 minus 2 times Ti plus Ti minus 1, right? And this should be it. So let me see if I got anything wrong. This I here should be lowercase. T new should be equal to Ti plus dt over dx squared times Ti plus 1 minus 2Ti plus Ti minus 1. Looks good. So this is our for loop. This is everything you're gonna write in your for loop. Pretty simple, right? And then we need to make sure to set what I talked about earlier, that T new should be equal to tnp dot copy T. Sorry, it's actually the other way around. And we're not going to do that now because we need to reinforce the boundary conditions. I forgot about this. We need to make sure our boundary conditions are satisfied, or our initial conditions are satisfied after every iteration, right? And now we can say that T equals np.copy T new, right? And to close the loop properly, we just say that T equals dt equals T, equals T plus dt. So the loop iterates properly, and then we just write return return T, temperature. Okay, good. Now we just set a variable here, final temperature. I can just close this now. Final temperature equals calculate temperature, and then I didn't define the parameters, right? God, I'm so dumb. So we used T final, dt, dx. What else did we use? We use nx, right? Nx. What else did we use? T, of course, and T final. What is the problem here? Sorry, it's T. Sorry, T new, not T final. T new. Nice. And then we just copy these parameters over here. We Control C, Control V. Nice, easy life, easy peasy lemon squeezy. And then we just plot our results, right? So from now on, your code may look a little different from mine, because I'm just gonna plot the results. So it depends on how you want to plot them. You can do just a temperature, like do a temperature function, and it will look like a sine function or whatever. I'm gonna plot the bar with a color scheme. Okay, so PLT here, fixed size equals. Since it's a bar, and I mean this like this code here that I'm doing, this line of code. You don't need this. This will just set the dimensions for the window that's gonna pop up when we plot the graph. So you don't need this. Optional. Optional too. You don't need this. Your code will run just fine. plt.show, and then this will turn our 1D array into a 2D array to be plotted properly. So we're just gonna say final temperature, and then we're gonna say, where is these? np.new axis. Just a command to make our 1D array into 2D array. Aspect equals 1. CMap. Your CMap can be whatever you want. I like jet, but it's a personal preference. You can use viridities, magma, cold and warm, or anything you want. Extend equals, and then we're just gonna write here. Wrong button, right button. 0 L 0.005. This will make our 0.05. This will make our bar actually look like a bar. If you change these parameters, it will make it look a little too squared for my taste. But I mean, you also, this is kind of optional as well, just to make it visually more pleasing. And that's about it. PLT dot title. So what will the title of our graph be? Probably 1D temperature field. We can also do plt.xlabel to make it presentable as position along the rod x, and plt.yticks. This is useful because this will take, like, it's optional as well. You don't really need it. This will just hide the y ticks on your graph. So it's a one-dimensional bar. And plt.show. Now, I never get these codes running at first time. So if it runs first time and something's wrong, it ran first time, but I think this is right, apparently, because our temperature function was sine np over 2 times x. So when x equals 0, the temperature should be 0, which is blue here, cold. And when x equals 1, it should also be equal to 0, right? Because it's going to be the sine of pi over 2, which is 1 actually. So it's cold here. Is it a domain should be 2 then for it to be cold? Let me try this now. No. Oh no, but I think it's right. Yeah, this is correct. Because of our boundary conditions, dummy dum. Boundary conditions, dummy dum. I'm so stupid, I forgot to look at the boundary conditions 0, 0. Yeah, it's correct. Yeah, you don't have to use this 1.0. The bar looks super thin because of this 0.05. If I want to make this the same, I just need to double this as well. This would be 1.0. Sorry, 0.1. And then I can just do this too. And it will look like a regular bar. It's just messing up with the dimensions. Yep. So length 2. So this is exactly what we expect because it peaks over in the middle here, which is what you expect from a sine function. So yeah, it worked out first try. Damn. Hot damn. Yeah, super easy code. Next video we're gonna look into the 2D version, which doesn't change a lot. I'm gonna use this code as a base. And so to summarize, we use the finite differences method. We used this equation over here, which is written here. This is the heart of our code. Setting up the initial conditions or the boundary conditions after the loop, copying the new temperature to make sure we always use the previous temperature to calculate the new one, and plotting the results, which is optional. You can do this however you like. There are different colors here as well. So yeah, I think that's pretty much about it. Thank you all for watching.